Okay, so I'm going to start from scratch. I've got the recording going now. Let's say that we have WaterGEMS installed. We've got the connection client, which is your way of proving that you have the permission to use the software. That's running off to the side. And so now we start WaterGEMS. And the first thing we want to make sure about is that the units are set to SI. And so by default, the first time you run the program, it's going to have BG. But I'm going to create a new hydraulic model. And I don't care to track the changes if it asks me about that. No. And so just to refresh your memory, it was here in the Tools options, and then More Tools. The Options menu is where we can go to Units, and you'll notice it says SI, and that's because the last time I had the program open just a moment ago, when it was in BG, I switched it to SI, and then I closed this project file, and you can start a new one. So it's in SI. That's the first preliminary that we always need to do. The next thing is we need to check the calculation method to make sure that it's using the Darcy-Weisbach equation. So here in the Analysis tab, see the Analysis tab, Options, and then the Steady State Solver, open up the Base Calculation Options, and it says Hazen-Williams. Now Hazen-Williams is an okay method for calculating pressure loss due to pipe friction, but it only applies to water at a certain temperature and over a pretty narrow range of pipe sizes and flow velocities. So it's not always applicable because you may have a pipe size that's smaller than is intended for use with Hazen-Williams. You may have warm water instead of cold water, which is what Hazen-Williams is assuming. And you may even want more accuracy than Hazen-Williams can handle. So Hazen-Williams is great if you're doing hand calculations, but frankly I don't know why it's even an option in this program, because I don't care if it takes the computer another half second longer to do the calculation. So instead of Hazen-Williams, in the drop-down box, what you should select is the Darcy-Weisbach. The Darcy-Weisbach equation is applicable over a much wider range of hydraulic and physical pipe diameter conditions. So it's more often going to be applicable, but then just on top of that, it's always more accurate. So select the Darcy-Weisbach in the solver. So the two things we've done so far is we made sure we were in the SI units, and then here in Analysis, Options, the Base Calculation Options for the Steady State Solver, we want it to say Darcy-Weisbach. Okay, so that's where we're at so far. Now, WaterGEMS has the option of being integrated with MicroStation, and none of you, I think, are civil engineering majors, but MicroStation is a pretty good CAD program for people in the civil engineering field. But I don't bother to integrate this program with MicroStation. I think it works great standalone. So this will be the view that you see. It still has some tools that will allow you to sketch things out, to draw the system that you want to represent. Now, in the handout I've given you, it shows a reservoir. I think I showed you this picture before, right, in the lecture? The idea of what if we just connected a water fountain straight to a reservoir. And if we know the water elevation of the reservoir, and if we know the elevation of the fountain, then we can calculate the pressure inside the fountain using the hydrostatic equation. And so you probably by now have memorized that the hydrostatic equation, delta P, is delta H times gamma. So the pressure inside this fountain is just going to be the difference between the water elevation and the physical elevation of the fountain. That would be the delta H. And then the unit weight, gamma, that we'd use, if we don't have any special information about the temperature, we just use our standard 9810. And we could calculate the pressure increase in there. So it's not like this software is going to save us too much time because the hydrostatic equation is easy enough, but it's if we wanted to make lots of little changes and optimize that it would begin to become more useful. So that's what I'm going to illustrate today. So one of the tools that we have here is this layout tool. And the layout tool is how you draw or represent the physical system. So left click on that layout button, and then when you bring the cursor down into the window, you'll notice that we've got a target and then a little circle to the side of the target. What that circle represents is a junction, meaning a place where two pipes come together or where a pipe terminates. But what we're going to do is we're going to right click, and it'll bring up a list of different options that you can choose from. And it's not a junction that we want. We want to start with a reservoir, because the first thing I want to put onto my little sketch is this reservoir that the pipe is connected to. So what I did was I right clicked, and then if you select the reservoir option, now you'll notice that that symbol that's to the lower right hand side of that target, it changed from a circle and now it looks like an open reservoir. That's what the little triangle at the top is showing, is that it's a free surface of water in contact with air. So now I left click to drop that symbol, and then as I move my cursor away, what it's doing is kind of just building like a conceptual diagram of the system that I want to create. And I'm going to right click again to change it from reservoir back to a junction. So now I've got that circular symbol again, and then I'm going to left click, and then as I move the cursor away, what I could do is I could drop another junction, but actually I don't need to. All I need to create to represent this system is on one side a reservoir and on the other side a junction. So now press the escape button and it will terminate drawing. Alright, so all that's just to draw a line. Anybody else manage to draw a line? Good? You're following along? Excellent. Alright. So this line has characteristics though. It starts off by assuming some things about the system. Oops, I didn't mean to do that. Alright, let me select it and delete it. Not that it would do any harm, but here in these flex tables we can look up the characteristics of the system, or you can use the select button, and if you double click on something it'll tell you about it. So let's just double click on the reservoir and see what it tells us about the reservoir. This list of properties that it's pulled up. The X and Y coordinates is referring to, this is like a top view of a system. And so we're looking down from above, and if you had a coordinate system like latitude and longitude or state plane coordinates or UTM or whatever, you could have these symbols located in a scaled map in the actual location where they're found out in the real world. For our purposes, we just kind of randomly dropped the symbols somewhere because it's just more of a conceptual diagram rather than a scaled drawing. So don't worry too much about this X and Y location, but there is one thing we need to pay special attention to, and that is the elevation that it says. And so from the drawing that you've got, it says that our reservoir is located at 615.47 meters. So I'm going to enter in that the elevation is 615.47 meters. And so now the system, the elevation of the source that the water is going to be coming from is in the program. And that's really the only thing we have to tell it about the reservoir. It doesn't matter, not from the hydraulic perspective, how deep it is. It doesn't matter the water quality that we could keep track of here. And those are things that in a real world they maybe would want to know how old the water is in any particular tank. But for us it's just the elevation that we're going to be defining. Okay, so I got the elevation that way. If I open up the flex table, just to show you what that looks like, the little triangle that's underneath the flex table, there's tables of all the different types of network elements, and I'm going to bring up the reservoir table, and what we'll see is just a single row because there's only one reservoir. And the only thing that we have defined is the elevation. You could change the name of the label. Right now it's called R1. If I wanted to, I could change it to say the reservoir, and then that is automatically and dynamically updated in the annotations. By the way, over here on the left side, I can choose which of the annotations to display. So for instance, here if I expand where it says reservoir, I could turn off the reservoir label like that. Or if I wanted to add annotations, then I can add them as well. And I'll show you that in a minute. But right now, this is saying like P1. Well, I don't need it to tell me that that's pipe number 1 because we've only got one pipe. So like that pipe annotation isn't adding a lot of value right now, so I might as well just turn it off. So by clicking that label next to the pipe annotation, then it switches it off. Okay, so we told it the reservoir elevation, and just to show you how to annotate, let's actually add a label of the elevation to that reservoir. So here under reservoir, if you right click, then what I want to do is I want to do new annotation, and then the annotation that I'm going to choose from, it gives you a list of options. The options that I want to have would be elevation. Okay, now if I just apply, it's going to be right on top of the reservoir, and that's not so good. So I can do an offset to bring it down. If I want it to be maybe above and a little bit to the left, then the Y of maybe 5 would bring it up. Maybe that's too much. Maybe let's try 3 for the vertical above it, and then I'll move it off to the side a little bit, maybe like -5 for the offset. So now I've got my elevation. And it would actually, the elevation is good, it's pretty self-explanatory, but here under prefix, maybe I should add an abbreviation like ELEV equals, and if I apply, now you can see it's got that. I need to maybe move it a little bit further over to the left since I've added the prefix there. Alright, so that's how you add an annotation. So now the water surface elevation is annotated. If we bring up the flex table for the pipe, you can see that what's known about the pipe? Well, the diameter is the default diameter that it assumed is 152.4 millimeters. In our problem statement, in the handout I gave you, it says it's a 5 centimeter diameter pipe. So we need to change what its default assumption was to be consistent with this statement, 5 centimeter diameter. So 5 centimeters is how many millimeters? 50. Okay, so I can put in 50 millimeters, or if I'm going to be doing a lot of data entry and I wanted it to be in centimeters rather than millimeters, I can change it so that it forces it to be input in centimeters. So if I right click on that column and units and formatting, then I can change it from millimeters to centimeters, and now that column will have the units that I'd like. Okay, so another thing that we know about this pipe, if we go to the problem statement, is that it is cast iron. What does it say in the program the pipe is made out of? Ductile iron. Different pipe materials have different head loss characteristics. Some pipes are smooth, and so you don't have as much pressure being lost in a smooth pipe as you would in a pipe that's really rough. So I want to change it from ductile iron. I'm going to go through this material library and go through the list of materials it knows about, and I need to switch it so that it says cast iron. Okay, so any questions so far? I mean, conceptually, what we're doing so far is pretty easy, but it's just finding the right button and being familiar with the menus that is maybe the trickier part. It's, the tricky part isn't understanding what we're doing, it's just finding the menus. Yeah?
Why does it say Hayes Williams C beside that? Does that have anything to do with those?
That's a really good question. Even though we've told it to use Darcy-Weisbach for its calculations, then it still has lots of columns that may not be applicable. So this Hazen-Williams C is a roughness coefficient that if it was using the Hazen-Williams equation, then this C value would tell it how rough the pipe is. So like if I change from cast iron to plastic, let's see if I've got PVC, I think that the C value would change. See how it's 130 there? Here under PVC, it knows that the Hazen-Williams C of that should be 150. So if I selected PVC, then it's changing this C value. But if we go back to cast iron, let me show you what it's actually going to use when it does our calculations. It's actually going to use this roughness height, the 0.0003. When it does its calculations, it will use that roughness height and a few other parameters to calculate pressure loss. So that's a really good question. Even though we're not using Hazen-Williams, it'll be on that list of physical properties. Okay, so what else do we also need to change? The handout said that the pipe has a length of 10 meters. Let's see if the program got that right. Okay, it says 37 meters. Do you know why it says 37 meters? Any guess? I mean, why does it say 37 instead of 50? Well, yeah, it's just based on where I clicked. Remember, there are XY coordinates, and down here in the bottom strip, you can see the XY coordinates for the cursor. And so just by virtue of where I dropped this other junction, it did the calculations and found out how long that segment is. So you have two options. One is if you want it to actually do the calculations based on 10 meters, you have to be really careful about where you click and make that segment actually a scaled length that's accurate. That's one possibility, is that the scaled length is accurate. But over here we have another option where it says has user-defined length. That's a way, if you tick that box, you're overriding its assumption for how long the pipe is, and you're saying, well, no, that scaled length isn't what I want to go into calculations. I just want to type in what the length is. And so the user-defined length now is where I can type in 10 meters and enter. And so now, if I was going to create some annotations for that pipe, let me do that. Let me add a new annotation for the pipe. And from this list of fields, I'm going to choose diameter. Okay, so I'll add the prefix D equals, and then I'll choose an offset that's below the pipe, so I'll do -3 and apply. So D equals 5 centimeters. There's my annotation. I'll do another annotation, new annotation, and I'll have it do the length. And so here in the field that I want, let's see if it has length user defined. Alright, so L equals, and then I'll do the offset, the Y offset of -8. Apply. Alright, length is 10 meters. Oh, maybe 8 was too much. I'll do 7. Alright. So the one last thing that we need to do is we need to identify the elevation of the endpoint. You know, our pipe, in the sketch, it says that the water comes out of the reservoir at an elevation of 588.36. So I'm going to double click on that junction and bring up its properties. Or you can put in the elevation through the flex table for the junction and find that the elevation is set to 0 to begin with, but I'm going to tell it 588.36. Alright, so now it knows the elevation there. And we haven't yet done any calculations yet. I'm going to add some annotations to the junction. First of all, I'm going to turn off the label because I don't care about it saying J1. But I'm going to add an annotation, a new annotation that gives me the elevation. So I'll scroll down to the list of options and I'll do here ELEV equals, and then it'll do the elevation and it'll have its units on there as well. So the X offset, I'll do maybe 4 to the side and -4 down. Okay, so there's the elevation, and I also want to annotate the pressure. So new annotation, and from this list of options I'm going to annotate pressure, and I'm going to call that P equals, and I'll do this one 3 units to the right and maybe 2 units above. Alright, so you say it says so far pressure equals not applicable kilopascals because it hasn't actually run the numbers yet. It hasn't done any calculations. But this green button on the Home tab, Compute, as soon as I click that, it's going to calculate based on the water being in the reservoir, filling the pipe, the elevation of the pipe length, the pipe diameter, the material that's in there. It's going to consider all the factors that apply and calculate the pressure. So I'm going to pause for just a moment and I'll walk around the class, and if you've fallen behind on anything or you need any help, I'll get a chance to assist you with that before we actually do the calculation. Alright, so some of you couldn't resist, and I like that urge. You're eager to find out the pressure. When you click Compute, it crunches the numbers and it finds that you've got 265 kilopascals. What does our hydrostatic equation say? You know, did we get anything different than we would have if we'd just done this by hand? So the delta H in the hydrostatic equation would be 615.47 meters minus 588.36 meters. Anyone with a calculator tell me what's our delta H?
27.11.
27.11 meters. And so delta pressure is 27.11 meters. Now the question is, what fluid is it assuming? I think that we can probably look at that in the options. Right now it's assuming water at 20 degrees Celsius. Okay, so water at 20 degrees Celsius, I think that it says the specific gravity is 0.998. So it's not 9810 newtons per cubic meter. The unit weight it's using in the calculations are 0.998 times 9810 newtons per meter cubed. So what is that if you've got the calculator? 0.998 times 9810.
9790.4.
Okay. So 9790.4 newtons per cubic meter. So when we multiply it together, the 27 meters of head and the 9790 for the unit weight, 27.11, 9790.4, 265.417. So that's consistent with what the computer did so far. 265.47, 417. 265.417 newtons per meter squared. Now it did it in, it reported in kilonewtons, and if we want we could change that. Remember, it was us that put that pressure annotation on there. So here at the junction, if I right click on the pressure annotation, I can edit, and I can change the units and the precision that the units are displayed at. let's not get hung up on that. But okay, so now on the back side of the paper, there's a series of questions that are being asked that starts to give you an idea of how this software would be useful, like if you wanted to change a lot of things and find out what's the effect. So for instance, it says in question 1, what would be the pressure in the drinking fountain if the reservoir contained 4 degrees Celsius water instead of 20 degrees Celsius water? So I just had opened up in the analysis options, steady state base calculation options. Down here, if you scroll down, we had water at 20 degrees Celsius. Well, what if it was actually, here in the liquid library, you can choose from other liquids. And so what if it was water at 4 degrees Celsius instead? So you change the liquid, select, you can close that. And then if I execute again, compute, it goes from 265 to now it's saying 266. So we'd have 1 kilopascal of additional pressure if the fluid was more dense at the colder temperature. All right. So what I'm going to do is I'm just going to pause the recording and stop talking for a little while so you can go through these questions and see what does the hydraulic model say about if you raise the reservoir elevation, or what if you put mercury in the reservoir instead of water, or what if you change the pipe length, and so on. So just experiment with some of those parameters, and then after some time doing that, then we'll take an initial look at what happens if you do account for pipe friction. You know, like what if suddenly we want water to start coming through the pipes rather than just static conditions. Because so far, we haven't told this computer how much water is going through the pipe. So if there's no water coming out of the system, all the calculations thus far are just based on static conditions. So after I give you a chance to work through this paper, we'll look at the more sophisticated and complex situation of what if we don't have a static scenario. Need to submit this week. So the lab that you turned in for today was a full report, right? You're not doing a full report this week. You'll be glad to know that all you really need to submit is screenshots of what you did, and then like it asks for a brief paragraph where you're typing an explanation for something. So let's say you create a blank document, and in question 1 it's asking what's the pressure if the reservoir has 4 degrees Celsius water. So if I want to demonstrate that that's what I did, I'd want to show this network, and I'm also going to bring up the calculation options, and somewhere on the screenshot I'm going to provide, I want to show the water temperature, so I'll drag that to the side, scroll down. Okay, so right now on the screen, it's got the pressure that I calculated with water at 4 degrees Celsius. So I'm going to press the print screen button on my keyboard. So print screen, and then over here in Word, if I do Control V for paste, there's a screenshot. So what you're submitting this week is basically, you put your name, student name, ENGR 319. This is Lab 3, WaterGEMS, Hydrostatics. All right, so question 1. What is the pressure when the fluid is 4 degree water? Answer 266 kPa. See illustration below. All right, so then in the screenshot, I can see that you did calculate 266. I can see that you had the correct fluid selected. All right, so now on question 4, it's asking what would be the pressure if it was a reservoir of mercury. So now I can change from water, pick out a different fluid. Now I'm going to select mercury, select, and compute. Now I have way higher pressure. You do a screenshot by pressing the print screen button, and then over here in your Word document, this is being now question 4, just skipping over it, like you would type in an answer for 2 and 3, but here in 4, question, what is the pressure if you switch to mercury? Answer, I'll paste that in. The answer was 3,602 kilopascals. 3,602 kPa. So basically you go through all of the questions in the document, and what you're turning in is just this Word document where you're pasting in the screenshots that proves you went through the process of solving a certain thing, then the answer, and then your free-form response that you're explaining the idea behind a certain change. So just a numbered document 1 through 11, and that's all you need to upload. I think once you finally get the software installed, you can basically do the lab and the write-up in an hour or less. Okay? Alright, so I just want to demonstrate what happens when we want to do flowing fluids. Let me switch back to water. I'm going to switch it out of mercury back to 20 degrees Celsius water. Okay, let me have it calculate again. Okay, so we're back to the baseline of 265 kilopascals. It's 265 kilopascals if no water is flowing through the pipe. But what if I actually wanted to have like maybe 10 liters per second coming out? So I'm going to add an annotation here. I'm going to, at the junction, I'm going to have a new annotation where I want to have the flow rate. So I will do demand. I'm going to just add the label Q equals. And then maybe for the offsets here, I'll do 2 meters to the side and -4 to get it. Now I better do -6. Okay. All right. So far there's no flow rate going through there, but let me open up the flex table for the junction, and I'm going to specify that 10 liters per second. The place you do it, yellow means you can't directly type into a field. That's what the yellow is. So I can't just directly say 10 liters per second coming out at that junction. So instead, here in the demand collection, if I click this ... the ellipsis that's to the right side of that box, I'm going to say that the base demand is 10 liters per second. And as soon as I put enter, it knows it, but it hasn't yet updated until I click compute. So watch what happens to the pressure as soon as I click compute. The pressure should decrease. And it did. So what that means is that if you have 10 liters per second coming out of the pipe at that location, then your pressure is going to be lower. It was 265 to begin with. So the type of question that this software can be really useful at answering is, for example, if you have to have a minimum of 200 kilopascals, then what's the maximum flow rate you could withdraw? So really easily, what I could do is I could open up the properties and I could keep playing around with certain demand flow rates and find out what is the resulting pressure. Maybe it'd be easier to do it through the junction table here. So if I change the collection, instead of 10 liters per second, what if I said 7 liters per second and compute? All right, so if I'm doing 7 liters per second, it's 266. All right, well, that means I could increase it a bit. What if I take it up to 8? 8, compute. The pressure is now 213. So you could iterate and keep changing the amount of flow rate and see how does that affect the pressure. Or if it turns out that this isn't 10 meters isn't going to get you where you need to go, you know, for instance, what if you knew that the pipe needed to be 500 meters? So here under the pipe table, my user defined length, instead of 10 meters, what if it has to be 500? And I'll calculate that after closing. So what's the pressure like if it's 500? Negative pressure. That's not good. So that tells me that the pipe needs to be bigger. The diameter's too small. So like if I still have to hit that 200 kilopascal pressure minimum, then what it tells me is that 5 centimeters isn't going to do it. Well, would 15 get me closer to an acceptable pressure? So I can change it to 15 centimeters, compute again. The pressure's looking a lot better at 15 centimeter. So this is a really useful tool for changing some parameter in your design and computing and then seeing like what are the pressure implications of a change that you made. So that's kind of like the long view of how the software would be used. I've kind of given you a lot of hints there on question 11, the bonus question. That's the only time this semester that there will be any extra credit. So if you do that bonus question, then you'll get 110% on the lab, which is great. All right. So that's really all I wanted to show you with WaterGEMS. You're welcome to stick around and continue working on these questions here in the lab. You can choose to do it on your own later on if you'd like. The submission for this, the Word document that you need to upload, that should be submitted to MU Online before lab next week. So you've got the full week to finish it up.